Hi guys, welcome to lesson 19-2 on page 331 in your book, The Radioactive Decay Experiment. So in this lesson we're going to be able to identify exponential functions given a table of values, and we're going to relate those exponential functions to geometric sequences. So like arithmetic sequences were related to linear functions, geometric sequences are related to exponential functions. So let's see what we got here with radioactive decay. In the late 19th century, the scientist Marie Curie performed experiments that led to the discovery of radioactive substances. Don't touch those, they're dangerous. A radioactive substance is a substance that gives off radiation as it decays. Scientists describe the rate at which a radioactive substance decays as its half-life. So hopefully you've heard of half-life before. The half-life of a substance is the amount of time it takes for one half of the substance to decay. So if you have a radioactive substance sitting around, it literally disappears after however long it takes. It becomes at least too small to see. So it can be, the half-life can be as little as 1/1000th of a second. So just like you put a block of that out, it's gone. You can't even see it. It can't exist in air. It'll disappear. And it could take 4.5 billion years for uranium to even divide into half its size. So there's a big range. So first question, we're going to look at radium. Radium has a half-life of 1600 years. So how much radium will be left from a 1,000 gram sample after 1600 years? Well, 1600 years is its half-life, so it will decay by half. So after 1600 years, you would have 500 grams left. And then how much radium will be left after another 1600 years? Well, cuts in half, so you'd have 250 grams after another 1600 years. So it's decaying very slowly. Suppose a radioactive substance has a half-life of 1 second, and you begin with a sample of 4 grams, and we're going to complete the table of values below. So after 1 second, we'd have 2 grams, and then 1 gram, and then half of that would be 0.5 grams, and half of that would be 0.25 grams, and half of that would be 0.125 grams. So it keeps shrinking in half every second. Use the amounts remaining to write a sequence. This is part B. Write a sequence with 4 as the first term. So 4, 2, 1, 0.5. Remember, a sequence is just a list of numbers. 0.25. Better make my decimals bigger. They're easy to miss. 0.125. What kind of sequence is it? Hopefully you recognize it looks like it's dividing, right? It's not just subtracting because it doesn't go down by the same amount every time. So it's dividing. It's dividing by 2, but remember we can only multiply. So it's geometric because it multiplies by what to divide it in half every time? Multiplies by 1/2. Alright, and then we're going to graph that data. So for 0 time, in other words, when we start out, we have 4 grams. These are the grams on this side. And then after 1 second, we have 2 grams, 1 gram, half a gram, half of a half, and half of a half of a half. Oops, half of a half of a half over here. So it keeps decaying at a steady rate, cutting in half as time goes by. So a radioactive substance decays continually over time. To show this, draw a smooth curve through the points that we plotted. So that's why I just tried to draw a smooth curve. Not that smooth, but I did my best. So next question is, will the amount of radioactive substance that remains ever reach 0? No, it never will, because it's just going to keep getting smaller and smaller and smaller. It's going to keep cutting in half. Just keeps dividing in half. Now this is like, I don't know if everybody was there, but the day we talked about what if I, for the rest of my life, every day walked halfway to the door, would I ever get there? And we decided no, I'd have to be able to get microscopic and you'd have to be able to see me at the atomic level because I'd be so tiny. But if I just kept walking halfway every day, I'd only get halfway there. There's an infinite amount of space between any 2 points, so you can split it in half. So that radioactive substance is going to keep dividing in half, dividing in half, dividing in half, and it might look like it disappeared to the naked eye, but if you could see small enough, it would always just keep cutting in half of the size that it was. So the reasonable domain and range for this function, domain in this case is time, so it would be the set of all x where x is greater than or equal to 0. 0 was our starting place. If you look back at our graph, you can see that it actually stops right there. It doesn't go any farther back than 0. And y value, the highest it ever went was 4, but it keeps getting smaller and smaller and smaller, but it never reaches to 0. So for our explanation here, domain is time and cannot be negative. And then for our range, the range is the set of all y where y, well, 0 is less than y, which is less than or equal to 4. So y never actually equals 0. So it's always greater than 0, but less than or equal to 4. So started with 4 and never reaches 0. That's why 0 is not included in the range. It only stays above it. What's the y-intercept? And that is 4, and it represents the amount to start with, the starting amount of the substance. So the function that describes that substance's decay is the exponential function f of x equals 4 times the quantity 1/2 to the power of x. So that means that the geometric ratio is 1/2, so 4 keeps multiplying by 1/2 over and over and over, which divides it by 2 over and over and over. Remember, to multiply by 1/2 means dividing by 2. So the graph, when it doesn't model a real-world situation, is shown below. So it doesn't have that restriction on time, so it can cross right over and it can go both directions. All the way this way, keeps getting higher and higher. This way keeps getting smaller, smaller, smaller. So recall that an exponential function is in this form. This is the form of an exponential function. A is the starting amount, and it can't be 0. B is the growth or decay factor, or the geometric ratio, the common ratio, and it has to be greater than 0. It can't be 0 or negative, and it also can't be 1, or it would just be staying a horizontal line. It wouldn't be growing or shrinking. So B has to be a positive factor, right? If it was negative, it would keep jumping back and forth between a positive number, a negative number, positive number, negative number. So it has to be positive. In order to shrink, it has to be a number between 0 and 1. And in order to grow, it has to be a number greater than 1. So what are the values of A and B for this particular function? A equals 4. B equals 1/2. So how are they related to the decay? This is the start amount, and it keeps, since it's a half-life, keeps dividing in half. How is this graph different from the graph you made in items 3 and 4? The domain includes, includes negative numbers, since we are not restricted by time. And otherwise, it's pretty much the same. How do the values of y change as the values of x increases? So as we go this way on the x-axis, the y values are decreasing. Y values decrease. And how do the values of y change as the value of x decreases? So as we go this way, the y values are going up. So the y values increase as x decreases. So they're kind of opposites in this case. That's what decay does. A bucket contains 16 cups of water. An amount of water evaporates each day. So again, this is something that's a decay function. Something's getting smaller. So the amount of water left in the bucket is a function of the number of days, n. Match each function with a description and tell whether the function you chose is linear or exponential. On each day, the bucket loses 1/2 cup of water. So that would be this one. A, we'll go with this one. So it's losing 1/2 a cup of water every day. So every day, you just minus 1/2 per the number of days. So that would be linear. Because it's got a constant rate of change, it's just going down by 1/2. By the end of each day, the amount of water in the bucket is half of what it was the day before. So that half of a smaller and smaller and smaller number. So that's going to be geometric. So that is this one. This is B. And that would be exponential. It's multiplying over and over by a factor of 1/2 or dividing by 2 every time. So I think you knew what evaporated meant. It becomes invisible. So this is your practice for decay. Everything's going to be multiplying by a number that's smaller than 1 in this case because, let me just make sure, but this should be because it's the decay lesson. Half-life, that's definitely a factor of 1/2. And this is reducing, yep, the value of your car is reduced by 1/2, so it's kind of like a half-life. And you can fill in this table and you can do some experimenting to solve these here. And then you can use that same problem you just did to answer this one. So figure out how many years it's going to take before its value falls below 500. Just some calculations there. When you're done, be sure to check the key. And then I need you to invest some time on this preview mix for tomorrow because it's long, but not only do you need to understand the concepts, but you also need to know how to use the graphing calculator on your computer. So I walk you through that in that mix also. So please spend the time being individually focused on what you need to get done so you don't get buried, and then we can pick it up from there tomorrow.